Hello and welcome back to part 4 of my operating system development tutorial. In this video we'll be switching into 32-bit protected mode so that we'll be able to use some extra instructions from the CPU and access a higher address space. Let's get started. Right, so this is where we left off. We have this extended program.asm loaded into the system and run. We don't need this stuff anymore, so let's just get rid of it. Get rid of this string and this function. And we need to define a new function, enter protected mode, which is 32-bit protected mode. And we can do well, we're never going to return from this, so it's not a function, it's a jump label. So we'll just jump infinite after that if it does fail. So we want to jump enter protected mode. Right, so now we can get rid of that. So now we are in enter protected mode. So entering protected mode, what do you have to do? You have to disable interrupts. You have to enable the A20 line. You have to load the GDT, the global descriptor table, and then you have to set it in a register so that the CPU knows where it is. Right, first things first, we need to disable interrupts. So CLI, that disables interrupts, pretty simple. Next, we need to enable the A20 line. Now the A20 line is a weird backwards compatibility thing. There's a lot of ways to enable it and test for it, but we're just going to do the simple hacky way of doing it. It works on most systems. It might have an error with a few systems, but for the purpose of this tutorial, it'll do just fine. So enable A20. And this one is a function, so we'll return from that. And to enable this, this is 3 lines of code. We need in AL OX92 or AL2 and then out OX92AL. So we're just taking in a value, doing some bitwise maths to it, and then shoving it back out. That's pretty much all we need to do. Right, now we have the problem of the GDT. Now the GDT is a structure that defines memory locations and memory sizes and privilege, stuff like that. So let's create a GDT. We'll create a new file so that we can just have it on its own. Let's call it gdt.asm. Pretty simple. So in order to set the GDT, we need to have a GDT description structure which contains a size and an offset. Now the size is the size of the GDT entry we are putting in, and the offset is the memory address of the GDT. Alright, so a GDT entry has 2 parts. Well, technically it has 3 parts. It has a null descriptor. It's a bit of memory that has zeros in it. This is just something that we need to add so that the system doesn't go crazy. I'm not entirely sure why we need to add this, but we do. And then it has a code segment and a data segment, and these just define memory areas for code and data. But we're not going to do anything fancy with that. We're going to set both of these segments to start at 0 and go to the maximum. So let's define a label for the GDT. So we have GDT null desc for the null descriptor, and that's just pretty sure it's just 2 double words. A double, and we'll declare another double. So that's taking up 8 bytes of space. Now we need to declare the GDT code segment. Now there's a lot of values we can put in here. The first value we need to define is the limit, which is 2 bytes. So we'll do a declare word FFFF, because we want our limit to go all the way as far as it can, so we cover the entire span of memory. Then the next thing we need is the base. So that'll be 2 bytes, and that'll be 0000. So we'll set the base of our code segment to the very first bit of our memory. The next part that we have to declare is the next part of our base address. So that'll be set to 0000 as well, and that's a byte, so we just put 2 zeros. So that'll keep our base at the very bottom of our memory. Now we need the access bytes. So, access bytes, we have the present bit. It must be 1 for a valid sector. Our memory is valid, so we'll set 1. The privilege, we're running our memory currently in the kernel privilege, so we set it to 00. It can go from 0 to 3, which is the highest at 0 and lowest privilege at 3. Then we need the descriptor type, and this should be 1 for code and data segments and cleared for system segments, but we're not worried about system segments yet, so we'll just set it as 1 for the entire memory limit. The next bit we have is the executable bit. This is 1 if it's a code segment and 0 if it's a data segment, so 1. Now we need to worry about the direction or the conforming bit. Now this is different depending on which segment it is, but we are defining a code segment, so we are worrying about the conforming bit. This is just to do with privilege and stuff, so we'll just set this as a 0, and I can cover that in a later video, or we can just leave it as is. The next thing we need is the read or write bit. For code selectors, we're talking about the readable bit. So we do want this to be readable because it's a code segment, we have to read it. So we want 1. And then the last bit is the accessed bit. We should set this to 0 and the CPU will set this to 1 when the segment gets accessed. There we go. That's the first amount of flags that we have to worry about. We put a B here so that it knows we are declaring a byte. Now we have to define the rest of the flag. So we'll define another byte, and the first flag we need to worry about is granularity. If it's set to 0, then the limit is in 1 byte blocks, and if it's set to 1, then the limit's in 4 kilobyte blocks. We'll set this to 1 so that we can set the value for a much larger region of memory. The next is the size bit, and if it's 0, then the selector defines 16-bit, and if it's 1, then it defines 32-bit, so we want 1. The next 2 are just 0, they don't correspond to anything, and then the next 4 bits of this byte is actually an extension of the limit, which is really strange how they've set this up, but it is what it is. So we'll set those all to 1 so that we can have the biggest limit possible. The next thing we need to worry about is the really high portion of the base. See, it's all like split up, it's really weird. But the base is set to 0, so we'll just do 0x00. Now for the data description, we just copy everything over except for the executable bit. The executable bit needs to be 0 because we're defining this as a data descriptor. So I'll just comment all these off. So that's the limit, base, low, base, medium, flags, plus upper limit, and then base, high. It's a really strange layout for the GDT, but this is what you got to do. Now we need to define the GDT descriptor, which is what we'll actually pass to the CPU register when we're passing the GDT, essentially. And what the GDT descriptor holds is the size and the offset, as I said at the start of the video. So we have the GDT size, which is, if we define a label GDT end, we can define it as GDT end minus GDT null descriptor minus 1, because the size has to be the actual size minus 1 for some strange reason. And this needs to be 2 bytes, so that's a word. And the next thing we need to do is a double word, so 4 bytes, which is the address of our GDT, which is this bit here. So we'll define that as GDT null descriptor. Right, and I'll just fix my spelling error here. Fix this up so it's a colon, not a semicolon, and that all looks good to me. Right, so we've got our GDT set up. Now we need to include it in our extended program. Before we move on to uploading our GDT address to the CPU, we need to define some constants. So we need to define the address of our code descriptor, which is simply GDT code descript minus GDT null descriptor. And we need the data segment, which is equal to GDT data descriptor take GDT null descriptor. So we'll be using these later on. I just realized back in enable A20, we need to put this colon here. Very important. And also fix my spelling of GDT end. Now what we have left to do is LGDT, which is load GDT, into our GDT descriptor. So that'll give it the pointer to this, which defines all of this. And then we need to set the bit of the CR0 register. So we'll move CR0 into EAX. We will OR EAX with 1. and then we'll move EAX back into CR0. And what this will do is we turn off interrupts, load the GDT descriptor, and then we set the bit so that it knows that it's in protected mode, 32-bit protected mode. Now, one thing to do before I forget is call enable A20. And also we need to do a far jump to flush the CPU pipeline. Now the reason we need to do that is the CPU can often be doing multiple things at once. And if it's doing something we don't want it to do, while we're doing the switch to this, it could produce unexpected results. So what we need to do is do bits 32, because now we're operating in 32-bit space, and we need to make a function. We'll call it start protected mode, and we'll just do infinite jump. So instead of doing infinite jump here, we need to do start protected mode. As I just said, we need to flush the CPU pipeline, and by doing that, we need to do what is called a far jump. So we need to change the memory segment, and that's pretty simple. We can just change it to the code seg, which we defined in the GTT file. See, code seg, we can jump there, make sure it's not capital, and then theoretically we should be here. Now the first thing we need to do before we do anything else is we need to point our segment registers to the new data that we defined in our GDT. So move AX data seg, and then into all of the segment registers we are moving AX. So we have DS, SS, ES, FS, and GS. Now we can also move the position of our stack to something way larger like that, but where the stack is for now is fine in my opinion. We're not going to be allocating much to the stack at the moment. You can set it if you want. It's just move EBP this, and then you move ESP EBP. That's just if you want some more space for your stack, but it's not required. Alright, now we can't use our BIOS routine to print to the screen anymore. We have to alter the video memory directly. Now, the video memory in text mode, which is what we are currently in, is located at 0xB8000. That's the start of video memory. So theoretically, if we move a H into this part of video memory, we will be able to see it pop up on screen at the first letter. Actually, this needs to be a byte. We need to specify that we're moving a byte into this pointer. It could be anything that we're putting in there, so the compiler needs to know. Let's compile and run it, and here we go, we have a H. Now I'll show you what that was before. We have what it was before, P, Plex 86. So, just like on the second video, we can create a hello world. So let's do that right now. Hello world. Right, and we'll increment this memory address. Actually, we need to increment it by 2 every time, because the odd numbers contain formatting for the characters. Right, so let's see what we get now. Theoretically, we should get hello world. Right, hello world. So we've created a hello world application in 32-bit mode. Yay! So in the next video, we'll be focusing on making some 32-bit functions and talking about some stuff, and maybe even doing the switch to 64-bit mode. So that's all for this video. Thank you for watching, and I'll see you next time.